I want to make some considerations on operators, quantum mechanics, and the Schrödinger equation. In particular, we start from a classical trajectory, and we start at some point where we have a Lagrangian. So this point will be given by the value of the Lagrangian of a certain Lagrangian of a classical theory. It will depend on the position x0 at time t0, whereas this point, the endpoint, will be given by the value of the Lagrangian at xf tf, let's say. So when we integrate all the values on such a curve, we get the action associated to this curve. And the change in the action would be equal to 0, because in general, to find the equations of motion, we have to set the variation of the action, and we set it equal to 0. So we find the classical trajectory, and let's assume that this is indeed the classical trajectory. Now we try to be a bit more general now, and we associate this trajectory with a certain state, which will be a quantum state, but we think that we have some state, psi, and you can think of that as a vector, and this state is associated to this classical curve. If we perturb the classical curve by some amount, now I'm exaggerating a little bit, but let's say that now we have a different state associated to the curve, which will be psi prime, and this will be given by psi plus some small change in the state psi. And we impose some conditions on such states, in particular that they are normalized. So the inner product between psi and psi is equal to 1. So we can interpret such an inner product as a dot product. So we have some row vector which multiplies a column vector, and in principle there can be an infinite number of components here. So this might also be seen as some kind of integral, but I will not get into the technical details here. And similarly, also this state here is normalized, which means that psi prime is equal to 1. So if you really want to have more details about this, you should cover some quantum mechanics. So you need to study some quantum mechanics, because it is definitely the physics behind these mathematical concepts, and it is impossible to cover that all in just one video. But for now, we are interested in these mathematical properties, and whatever this psi is, this state, it follows this property. So it is a normalized state, so its inner product is equal to 1, and similarly psi prime as the following inner product, which is equal to 1. So they are called normalized states because their inner product is equal to 1. In order to move from this curve to this curve, we act with a certain operator, and the operator will be a function of the operator which generalizes the change in the action. So we call it delta S with this at to denote the fact that we define this operator delta S, and I will say more about this in a moment. And by means of this infinitesimal action operator, we move from this curve to this curve here. So we move from the state psi to the state psi prime, but we have to remember that we need to preserve the inner product. So we need to preserve the following properties when we do such a transformation. So when we move from one classical curve, so from one curve to another curve. Now, in order to preserve this property, we define psi prime as some operator which will be of the following form, e to the I, and then here I put delta S, because remember that in order to move from one curve to the other, we have this operator related to the classical action, related to the action. So we have this operator which is like the quantum version of a small change, a small perturbation of the classical trajectory. And if we want the argument of the exponential to be dimensionless, which we need to require because otherwise it does not make sense, we divide by h bar, which has units of action. This is the Planck constant, and it has units of action. So it makes sense to divide delta S by h bar. And we place it in the argument of the exponential, and then we act on psi. So when we want to compute the bra version of this vector, which is the ket vector, so this is called the bra ket because this is a bra and this is a ket. So it's the bracket notation in physics, and in order to calculate the bra from the ket, you have to take the transpose and also the complex conjugate of that, and this is defined as the dagger. So it's this operator here, the dagger, and it means that we take the transpose and the complex conjugate or vice versa, which is the same. We can take first the complex conjugate and then the transpose. So when we take the dagger of this expression, we get psi written like this as a bra, and then we have e to the minus I when we take the complex conjugate of I, and then we have to take the dagger of delta S, which is the operator there. And in principle, you can show that when you have the exponential of an operator and you take the dagger, you really have to take the dagger of the operator, because you can think of the exponential as a series. So it's something like this, a to the n over n factorial. And then when you take the dagger is a linear operator, so you will really have to take the dagger of this. And this means that you are going to take the dagger of A, like this. Now, if an operator is Hermitian, then this delta S would be equal to delta S without the dagger. And in physics, if we have an operator such that its dagger is equal to itself, then the operator is said to be Hermitian. And Hermitian operators have very important properties in physics. I will dedicate a video to them in the future. Now, it's not really important in this video to know that an operator is Hermitian here. And why is this transformation important? Well, because it preserves this inner product here. Because when you take the inner product of psi prime with itself, we get the following thing. We get psi, and then we have e to the minus I delta S over h bar. Here we have e to the I delta S over h bar psi, and this is the identity. Therefore, here we get that this is equal to psi psi. So it means that the inner product is preserved, and if this is normalized, meaning that it is equal to 1, then also this one is equal to 1, of course. Now, at this point, let me rewrite this state, psi prime, which is also equal to psi plus delta psi. Remember that we have defined psi prime in such a way that we move from psi to psi prime by means of this operator here. And since we are considering small changes, it makes sense to replace the complex exponential by means of its Taylor series expansion, and we can truncate it to first order. So we get something like the identity plus I delta S operator divided by h bar acting on psi. And from this equation, we get that the change in psi is equal to I delta S over h bar psi. If you want, we can multiply by h bar and also by minus I, so here we get a factor of 1 on the right. And since we consider the state psi to be a function of position and time, the change in psi can be written as the change in time and then we take the partial derivative with respect to time, plus then we have the change in the position, dot product with the gradient acting on the state itself. So here, if we multiply this by minus I h bar, this must be equal to the change in the action, written as an operator. Now remember that in classical physics, the change in the action can be written as momentum dot product with the change in the position minus the Hamiltonian times the change in time. So now we promote this momentum to an operator and also the Hamiltonian here to an operator and here the action to an operator. So we can rewrite this change in this manner: P dot delta x minus h delta t, and then here we have the state psi. Now if we compare what we have on the left here with what we have on the right, you see that in order for these terms to be equal, what multiplies the change in time, which is minus I h bar d over dt, should be made equal, or actually in particular, this quantity acting on the state psi should be made equal to this quantity acting on the state psi. So this is not a quantity, this is actually an operator, to be more precise. So we have minus h bar acting on psi. Let's change the sign. So let's put it as a plus. And then we can do the same thing here on the left with what multiplies delta x. So we have minus I h bar, the gradient acting on the state psi. This must be equal to the momentum operator acting on the state psi. Now, these conditions tell us that in the quantum theory, the energy operator, which is related to the Hamiltonian operator, is given by this expression, IH bar d over dt. And the momentum operator, so the operator associated to momentum, is given by minus IH bar times the gradient. And this equation here is none other than the Schrödinger equation. In particular, the Hamiltonian, if we have a system which is characterized by just one particle, is given by the operator related to momentum squared divided by twice the mass of the particle. So let's assume that there is no potential energy. We only have kinetic energy of the particle. So the energy, the total energy is actually given by just the kinetic energy. And since you have to remember that the momentum operator can be written like this, then this will become equal to minus h bar squared divided by 2m, and then here we have the Laplacian, which is just the dot product between the gradient with itself. Then we get exactly the Schrödinger equation for a free particle when we replace h bar with this. So we have I h bar d over dt psi, and this is equal to minus h bar squared divided by 2m del squared psi. So this is the Schrödinger equation for a free particle, which is subjected to zero external forces. So there are no external forces, so there is no potential. For a particle with a specific momentum, let's call it Pn, and a specific energy, let's call it En, we have the state psi n, and a simple solution is given by a constant which multiplies the exponential e to the minus I or plus I. It's not important, the sign here. We have minus I and then something like this, p dot x, and actually we have to put the subscript p sub n because we have to find its momentum to be p sub n, the momentum of the particle, minus e sub n t divided by h bar. So this h bar is important because it makes this quantity dimensionless, and h bar as units of p dot x or e times t. So h bar as units of energy times time or momentum times space. Actually, let's choose the plus here, because when you substitute it into that expression, it's quite easy to calculate. So if you replace psi with psi sub n and you substitute it there, and what you get is basically that E sub n must be equal to P sub n squared divided by 2m, which is indeed the usual classical equation for the energy of a particle, because the energy of the particle is equal to momentum squared divided by 2m. And for a generic state, which is characterized by different particles, so you might have different momenta and different energies, and in principle you might also have different masses, so this can be generalized. A generic state psi can be written as a superposition of such states. So you have something like this, you have a summation over n, some coefficient psi sub n, and then you have the state psi sub n. And the original Schrodinger equation with a slightly more general Hamiltonian would still be satisfied. And these coefficients, a sub n, which might be complex, so they are not necessarily real numbers, actually they are complex numbers, so they have a real part, an imaginary part. By imposing the fact that the inner product between psi and psi is equal to 1, and also the fact that psi sub n, this inner product is equal to 1, and the fact that the inner product between psi sub n and psi sub m with different integers, so let's assume that n is not equal to m, this is equal to 0, meaning that there is no overlap between such a state with such a state, so they are completely independent states. To get some more intuition, you need to study some quantum mechanics to get a feeling of this, but these conditions impose some other conditions on these coefficients. Now, I will not write down the formulas, but you have some conditions on these coefficients that need to be satisfied.